But next up, we're going to hear from Neil Ganju, who's going to talk to us about geospatial metrics to guide restoration and damage assessments in coastal marshes and beyond. So just by way of introduction, Neil joined the USGS in 2001 at the California Water Science Center, and then he joined the Woods Hole Coastal Marine Science Center in 2008. He's a research oceanographer and leader of the Estuarine Processes, Hazards, and Systems Project, which applies observational, modeling, and geospatial techniques to develop a mechanistic understanding of estuarine and wetland processes and decision support products for management and restoration. Neil, thanks so much for joining us. Over to you.
Absolutely. Thanks so much for having me. It's a pleasure to be here to present our work. This is a collective effort across many USGS offices and mission areas, but primarily myself, Keaton Zafir here in my office, and then Brady Cuvion, who's down at the work in Louisiana, and Brian Lamb, who's down at the Lower Mississippi Gulf Water Science Center. So today I'm going to be talking about some of the work we've done on bringing kind of a geomorphic understanding to salt marsh vulnerability and showing how we've developed metrics to help guide restoration damage assessments. And then I'll show some kind of targeted applications of those data for the kinds of things that the NRDAR process, the NRDA process, and NRDAR would be interested in. So it's always good to start with just a little bit of background. I know everyone here knows why salt marshes are valuable, but it never hurts to repeat. So when you think about just from a safety to communities aspect, we know that salt marsh vegetation dissipates wave energy and surge. So the example on the right from a paper in 2017 looking at Hurricane Sandy impacts showed how effective marshes are, shown in green on the right, were at dissipating storm surge and waves just by the virtue of their stems, right? Their plant stems break up wave energy and then reduce the actual water level incurred by the surge. And that ends up avoiding losses in these counties, as you can see here on the right, shown in red, where red colors are indicating quite a bit of mitigation of loss. Marshes actually also turn out to be more resistant to storm impacts than beaches. Beaches don't have any root structure holding them together, so you can see large amounts of erosion from a storm that you would not see in a marsh. From a recreational perspective, we know that a large fraction of commercial species in the United States spend their early years in salt marshes. These are nurseries. And then in terms of economic values, it turns out bird watching and duck hunting are actually the top economic value of salt marshes because of folks who go to watch birds and spend their money on duck hunting. And then more relevant these days, when we think about coastal risk, when we think about navigation, we think about energy transport, the Corps of Engineers is spending a lot of effort on dredging navigation channels, and they need a place to put those sediments. So when you think about beneficial reuse, marshes end up being a very natural place to optimize that. And there's kind of a growing realization that marshes are part of a coastal sediment budget. Historically, we would think about the inner shelf, we would think about the coastline, we would think about beaches. Now there's sort of a growing realization that we need to be thinking about sediment from an ocean to watershed point of view, and considering marshes in that coastal sediment budget. So the general overview of what I'm going to talk about today, I'm going to kind of give this mechanistic link between salt marshes in terms of vegetation and the sediment budget. So kind of a different way of thinking about them. And I'll show you how we've done that. And then I'll talk about the metrics we've developed using those understandings. And then lastly, some of the applications for restoration and damage assessment, which would be of interest to this group here. So when I talk about salt marshes, I kind of attack it from this geomorphic perspective about if you're looking down at a marsh or you're on it, what's contributing to its trajectory. So very simply, on the seaward edge of a marsh, we have edge erosion, and that's controlled by waves, both from storms and just regular everyday wind wave action. And how the edge erodes is a function of that wave energy as well as the geotechnical properties of the marsh. Migration at the upland edge, where marshes are starting to migrate into forests and agricultural lands with sea level rise, is actually much more complicated. There's still quite a bit of research ongoing about what controls those rates. It's a little bit of slope, it's a little bit of adjacent land use, it's a lot about groundwater salinity, canopy cover, light penetration. So we're still working really on understanding those mechanisms. And then in terms of internal deterioration, which is what we're going to be talking about today, that's about the actual loss of marsh plain from within. And that can be caused by things like a contaminant release. It could be caused by salinity intrusion, invasive species, invasive rodents, crabs, salinity, I already said salinity intrusion, sediment deficits, sea level rise. And all of those are also kind of complex interrelated factors, but ultimately you diagnose them by loss of marsh plain, conversion to open water, and loss of elevation. So when we think about internal deterioration, we think about it very simply, almost as an accounting exercise. So a marsh, its whole system is really interconnected. It's not just the marsh plain, it's also the adjacent mud flat and the channels. All of those represent kind of a sediment account balance of sediment that's in the system. And then due to sea level rise, due to waves, due to tidal action, you have withdrawals and you have deposits. And some of those are shown here. And the hypothesis we set out with about a decade ago was that if you could measure the sediment budget of a marsh, you would know which way it was headed. So if a marsh is importing sediment and adding to its account balance, then it can keep up with sea level rise. If it's losing sediment, then it's in a deficit condition and it's withdrawing sediment from that account balance, and ultimately it will contract. And this plot on the right here is from a kind of large modeling study that basically showed that marshes are never really in equilibrium. They're always kind of changing in response to sediment supply and sea level rise. And there's actually a very narrow parameter space where marshes are just kind of standing still. That's not their normal behavior. So when we wanted to tie sediment budgets to internal deterioration, what we went out is we measured sediment budgets and internal deterioration. So at 8 sites around the country, we measured salt marsh sediment budgets using acoustic and optical sensors. And that's what's shown here on the right. Each one of those dots is one salt marsh complex somewhere in the nation where we had measurements from several months to a year at high resolution of sediment fluxes. On the x-axis is an independent metric from remote sensing called the unvegetated vegetated marsh ratio. And this is simply looking at that control volume of that salt marsh and then analyzing with aerial imagery what fraction is unvegetated, what fraction is vegetated, and dividing those two. And what we see, first of all, is a very strong relationship. And what this relationship is showing is that as you have more unvegetated area, as you move to the right along the x-axis, you tend to see sediment export. As you have more vegetated cover and you move to the left, you have less sediment export and you go towards a neutral sediment condition where you're neither exporting nor importing. And conceptually, this makes a lot of sense. If you have a healthy marsh plain, then you shouldn't be releasing sediment. You're sort of trapping or in a neutral condition. If you have a loss of vegetation due to one of those stressors, again, whether it's salinity, contaminant release, invasive species, now you've lost vegetation, you've liberated sediment from that area, and you're allowing for less trapping. Now, the other thing you see in this plot is that there's a stability value somewhere around 0.1, and that becomes important later when we look at that value in the context of establishing vulnerability. And what this looks like from that aerial imagery is something like this. So on the top left, you have a marsh at about 0.1, so the orange is vegetated plain, and the blue is unvegetated. In the middle is about 0.4, and then on the far right is a UVVR of 1, so that's half vegetated, half unvegetated, a very unstable complex that's losing a lot of sediment. So now I'm going to talk about how we extended those metrics into a broader geospatial context. So this concept of the UVVR, this unvegetated vegetated ratio, we decided, okay, this is something we need to map everywhere. So we started in the Northeast, and so here's just a marsh complex in Chesapeake Bay. And the workflows here on the right, I'm not going to spend a lot of time talking about it, but we basically break the marsh up into individual tide sheds, and we call these marsh units. And so these are the same way you would do a watershed analysis on the landscape. It's the same thing, but done on marsh units. So these are all geomorphically and hydrologically connected. And then we use aerial imagery to break those individual 1 meter pixels into what's unvegetated and what's vegetated. And then we can aggregate those up to get that UVVR score. So again, anything above 0.1, 0.15 is considered unstable and in a bad condition. So that's that lightish green, white to pink color. And so you can see, for example, this marsh unit all the way here on the far right, lots of unvegetated area. It will tend towards instability, whereas these other complexes on the far left in all green are at that very stable value of close to 0. Now, what we've done is we've mapped that almost across the whole Northeast. This is something we've been doing over the last 8 years or so, and we're almost complete with the entire Northeast. Chesapeake Bay alone is 45,000 marsh units. Each marsh unit is something on the scale of about 5 acres or so. So we have 45,000 in Chesapeake Bay, and then all these other systems have several thousand each. And on those units, we've mapped the UVVR again, which is this key vulnerability metric. We've mapped elevation of the vegetated plain using LiDAR, the tide range using hydrodynamic models, marsh lifespan, which I'll get to in a couple slides here, and then migration potential, which I won't be talking about today. So then we went a step further and decided we want to do this nationally. Now the marsh unit process is quite intensive, so you can't really do that everywhere quickly, but you can use satellite data to get the UVVR on a 30-meter pixel. So we've developed that data set for the 38-year period of Landsat, 1985 to 2022. I'm going to be showing some applications of that. And again, this is all publicly available, and I'll show that to you at the end as well. Now, the lifespan concept is really powerful. So here's a marsh in Jamaica Bay, New York in 2007, and you can see pretty intact vegetated plain. There's a little bit of unvegetated area right here in the middle, and certainly a little bit of fragmentation here. And what we do with this lifespan method is we take the vegetated fraction, whether from either of those methods that I showed you, we take the elevation and we calculate how much sediment is in the account balance. So that's how much sediment is under the marsh plane. So it's kind of locked in place, and that's your account balance. And then we use a couple methods to calculate the withdrawals, and that's withdrawals through open water conversion, which is a function of that UVVR, and then the deficit induced by sea level rise just rising on top of that marsh. That's inducing another deficit. So those are withdrawals. If you take an account balance divided by the withdrawals, you get a time scale, and that's what we call the marsh lifespan. And conceptually, what that's telling you is when your account balance of sediment that you have locked in place is getting drawn down to feed the rest of the complex and try to keep it above mean sea level. And so this was that marsh complex in Jamaica Bay in 2007. Here it is in 2025. You can see this is all mud flat now. You can see a lot of edge erosion that happened here on the left. I'll go back so you can see that marsh loss. And then sadly, here's what it actually looks like on the ground. And so this is one of our collaborators from the Park Service. I had made a cartoon showing something like this happening at one of their measurement locations. And sure enough, he went out to one of his sites and took this picture where this is essentially now a marsh complex with nearly zero lifespan. So everything you're seeing here, that's basically an intertidal mudflat, used to be vegetated plain, and that vegetated plain was cannibalized to keep the rest of that mudflat as close to sea level rise as possible. And now we're at basically a zero lifespan. So now I'm going to show you how we can apply all this understanding to actually look at restoration and damage assessment for establishing baseline conditions, quantifying injuries and recovery, and then estimating project costs if you're trying to restore a wetland marsh unit or complex. So here's a well-known example, post-BP oiling of salt marshes, which caused a little bit of loss in certain areas. So from this paper in 2013, we know there was a hot spot in Barataria Bay, and you can see it here on the left where there's a heavily oiled portion of Barataria Bay. This is the zoom in of that area here on the right. And then in this black box is kind of the control oiled area, which I'm going to be showing you. So we know that salt marsh vegetation will fluctuate. It can fluctuate due to water levels, somewhat due to storms and salinity dieback, possibly due to invasive species. But of course, for damage assessment, you have to establish baseline conditions and what the natural fluctuations may have been. So with this data set, this Landsat data set, we can do that for the 40 years of the Landsat record. So in the next plot, I'm going to be showing you the vegetated fraction of this black box you see on the right as compared to the entire box you see on the right. So here's that total vegetated fraction. Again, the red is just that control box I showed in Barataria Bay. The blue is the whole domain. So you see these are tracking pretty well together. So whatever's happening naturally across that whole domain from 1985 onwards seems to be happening in the oiled area for the most part. Now, if you actually know about events that happened, you can see the loss due to Hurricane Katrina that looks like it happened uniformly between those two areas. But then post BP 2010, you can see that the oiled area actually did suffer significantly more loss than the domain as a whole. So this gives you sort of a way to compare baseline conditions and reference conditions from the whole area relative to the small area that was actually affected by oiling. Now, another aspect is looking at restoration tracking and dieback and putting those into dollar values. So on the top here, we have Prime Hook National Wildlife Refuge in Delaware. Post-Hurricane Sandy, $38 million was invested to restore this area through aerial reseeding, hydrologic modifications, removal of culverts, and sediment placement. And with the Landsat data, we can actually track that gain in vegetated cover, which turned out to be about 1,000 acres on this 4,000 acre project. So that comes out to about $38,000 an acre. And given a marsh value of $7,000 an acre, which is one estimate from the SASB initiative that tells you that your investment return is about 6 years. So in 6 years, you've made back that investment in terms of storm protection, carbon sequestration, habitat provision. Conversely, we can look at impacts from storms. So down here are the Everglades National Park. Now these are mangroves, these are not coastal marshes, but we can still track change in vegetated cover with these data. So Hurricane Irma blew through in 2017. Before that, we had pretty stable cover, as you can see in 2014, 2016. And in 2018, we have about 1,000 acres of loss of mangrove vegetation. And so at a cost of about $80,000 per year of value that mangroves provide, you can now quantify that storm loss at about $80 million a year until those mangroves are restored or until they eventually reforest themselves, if possible. So lastly, the marsh lifespan concept is really helpful for looking at restoration. So for example, here is a marsh unit in Chesapeake Bay, outlined in white, you can see, and the areas under it that are a little darker, those are unvegetated areas. So this is a marsh unit that we've mapped. It's about 13 hectares. Now we can run our lifespan calculation under a given sea level rise scenario. So again, we're looking at the account balance of what's under the marsh plain relative to sea level rise and open water conversion losses. So when we run that model, that's in red. This is just what would happen with sea level rise. And we see that it starts out at 13 hectares. And after about 57 years, that marsh plain is completely gone, either due to open water conversion or submergence. Now, in my model, I can put in a restoration condition. So what I've done here is I've said, okay, 40 years in, we're going to do a thin layer sediment placement project at 20 centimeters, and we're going to revegetate 10% of the unvegetated area. So when I do that at 40 years, you can see this bump up in marsh area, and we get almost back to our original condition. But then with sea level rise increasing, we now see that we die off before the next 40-year interval. So at 75 years, the marsh is gone if we're waiting every 40 years. Now, conversely, I can do a 10-year restoration interval where I'm doing 5 centimeters, so 1/4 of the effort, and I'm revegetating 2.5% of the unvegetated area every 10 years. So of course, you have to balance out the costs of mobilizing every 10 years, but you can see what happens is if you do an action every 10 years, you now kind of maintain it pretty well until sea level rise really accelerates about 70 years from now, and now you die off at about 100 years. So what you can see is with a quadrupling of the frequency, a quarter of the actual restoration action, you end up expanding your lifespan by about 25 years. And so you can balance that with the individual properties of this marsh unit in terms of the values it provides and decide whether that additional effort is warranted or not. So again, in review, basically what we've done is we've made this mechanistic link between salt marsh coverage and sediment budgets to kind of give a geomorphic perspective about where marshes are headed. And with these metrics we've developed, we can establish baseline conditions, we can look at injuries and recovery, we can estimate costs of restoration and cost of return to baseline. And if you hit this QR code, it will take you to all these data products, both the national products, as well as the local products, as well as the marsh lifespan estimate and calculator. And with that, I'll stop and take any questions, and I thank you for your time.
I am not seeing any messages in the Q&A. Is there anybody who wanted to come off mute and ask or has something for Neil?
See lots of applause.
Thanks for the applause. I appreciate it.
Yeah. Yeah, very nicely done. This is a great presentation.
Good, thank you.
I really appreciate this lesson on the role and dynamics of salt marshes and watershed sediment budgets. These are some great concepts. I also love how this informs our understanding of baseline. So thank you for pulling that in.
Absolutely.
It fits exactly like you said for our damage assessment and restoration work. And I also really appreciate how you laid out that concept of a return on investment from the restoration at Prime Hook, Delaware. Very, very concise and insightful.
Appreciate it.
Nicely done.